My talk is about Galileo and the humanities, and I want to say that the mathematical style that Mark referred to was both born from the humanities, but also bequeathed a legacy, which is a challenge to the humanities, a legacy that it's still struggling with. And I have to say, when I wrote this a few months ago, after Mario invited me, I wrote a little bit. Well, a lot about Peterson's book. I had no idea that he was going to be here, so I'm really, a little bit intimidated that he's now here. The person whose work I wrote. I had actually just reviewed the book after I wrote this. So with Galileo, everything changes. He transformed and reworked insights and practices of his predecessors so quickly and with such an originality that 4 centuries later, science historians still look back on, still find this breathtaking and uncanny. As Mark puts it in his book, something mysterious happened. And his book does much to explain that mystery, to understand what might be called the Galilean moment. Now, historians tend to reserve the word moment for special turning points in which a radically new idea recasts past tensions and contradictions to open up new possibilities for the future. And Galileo's work certainly does that. It certainly counts. His greatest contributions did not involve lenses, pendulums, or mathematics. His most revolutionary act, what's at the core of the Galilean moment, was to help usher in a way of looking at the world in which we can look at the heavens with lenses, think of its chandeliers and swings as pendulums, and read its book in the language of mathematics. And that's more than a scientific development. That's more than just a collection of scientific developments. It involves a cultural transformation. From the time when math was viewed as just an interesting logical system to being the text of the world. That's at the core of the Galilean moment. That's what's mysterious. Now, the character of the Galilean moment has been obscured by a mythic account that's overly concerned with Galileo's Copernicanism and with his personification of the conflict between science and religion. All these things distract from what the real character, the real originality of Galileo, I think. So this myth not only distracts attention from his true legacy and that of his students, including and especially Kepler, none of whom, as Mark points out, specialized in astronomy, but skews and obscures an understanding of his writings and relationships. And it obscures as well, I think, that his understanding, our understanding of how the humanities relate to Galileo's work, and in 2 ways. Now, as Mark points out in his book, Galileo's Muse, Galileo transformed mathematics from what was essentially a branch of philosophy and theology, studied by artists and humanists, into a tool for scientists and a science of the world. Galileo was able to take this step, and this is the first part of what I want to point out, thanks to his deep and extensive training in the humanities. So this is a first way in which the humanities relate to the Galilean moment. But if the humanities were a legacy that made the Galilean achievement possible, that achievement, helping to usher in this mathematically saturated way of looking at the world, now posed, in turn, a fundamental challenge for the humanities itself, namely how to characterize the relation between that world and our own, science and the life world. This is a second way in which the humanities are connected with the Galilean moment. And the humanities, I think, are still struggling to cope with that challenge. And that struggle, I think, will eventually force the humanities to have to rethink their role and their practices. Now, many chapters of Mark's book clarify the first way in which the humanities are connected with the Galilean moment. And these chapters concern what amounted to the various custodians of mathematical knowledge at Galileo's time. These custodians included musicians, architects, painters, and even poets like Dante, well versed in the classics. In fact, one of his most striking illustrations involved Dante, who invented a new kind of topological space derived from a proof of Archimedes called the three-sphere, to depict the structure of the universe at the climax of the Paradiso, using it as an extended metaphor, Mark says, for the union of the finite with the infinite, the human with the divine. Renaissance painters were also custodians of classical mathematical knowledge, and just prior to Galileo were beginning to realize its deeper potential for their craft. These included Piero della Francesca, perhaps the first painter to utilize the vanishing point with what Mark calls subtler intention. And there's an amusing part of Mark's book where he calls Piero's book Di Prospettiva Pingendi an unreadable masterpiece. But fortunately, Mark reads it for us and makes it intelligible, and its significance and influence intelligible, and it accounts for why it's been so important. By the 1500s, in short, a fundamental shift in attitudes about mathematics was brewing. As Mark says, mathematics was now worth stealing. And then he shows how Galileo's deep and extensive training in the arts and humanities groomed him into being the thief. Galileo's background in arts and humanities, Peterson writes, was formative for his approaches in mathematics and emerging sciences. Yet its significance for scientific thought, while often acknowledged, remains largely unexplored. So Galileo's knowledge of perspective theory, for instance, was essential for allowing him to recognize what he was seeing in his telescopes. And you remember there was a lot of controversy about whether you could see, when you looked through a telescope, you could actually trust what it was you were seeing. And a lot of Galileo's knowledge of perspective gave him confidence, gave him the trust that you could look through those, and this wasn't just, what you were seeing wasn't just an artifact of the telescope itself. So with Galileo, Peterson argues, geometry comes to mean something it had not since the Greeks, a possible representation of a worldly structure and a sign of the world's intelligibility. And the symbol of this change is the parabola. The parabola, a curve of Greek geometry, Mark writes, becomes a metaphor for something physical, the arc of a projectile. That's the key move. More generally, Mark writes, all geometry became, potentially at least, a metaphor for nature, promising that nature could be understood as geometry could be understood. So while Ptolemy had confined mathematics to the heavens, with Galileo, mathematics broke out of its confinement, becoming also the science of the earth. So it was the meaning, Mark concludes, it was the meaning of mathematics that changed over the Renaissance, not the formalism. Actually, though, one of my favorite parts of Mark's book concerns the golden ratio. I'd always wondered, who was the huckster who got this hype about the golden ratio started? How did the cult of the golden ratio get started? And actually, Mark, one of the fun parts of the book is you actually learn how, which involves Pacioli and who even recruits Leonardo in this. It's a really wonderful part. Okay, but the dramatic high point of Galileo's muse is Mark's reading of Galileo's rarely discussed treatise, 2 lectures to the Florentine Academy on the shape, location, and size of Dante's Inferno, given in 1588 while Galileo was under consideration, this was a job talk, for a mathematics professorship in Pisa. And Mark just spoke a little bit about it here. He told about it here, but it's also a wonderfully told section of the book. And Galileo analyzes the architectural details of this part of the Inferno as they appear in Dante's poem, which is a popular topic of the time. But he realized, as Mark said, that Galileo realized that he had blundered afterwards involving the scaling laws, which would have been politically costly. He wouldn't have gotten the job if it had been uncovered. So he didn't publish the talk, set about trying to fix the error, and in working out the correct mathematics, he used a worldly analogy, a physical dome, to correct the statements about the mathematics of an unworldly structure. So he had therefore followed the traditional path of applying mathematics to something eternal and divine. That's the traditional part, the heavens as they appeared in the poem. And yet, Mark says, innocently, by accident, almost without thinking, he did so by applying geometry to the physical world, to our world, as an analog. This is the key point. This is the subtle point that's so beautifully laid out in his book. What Mark just called an example of stunning generality in Galileo's work. Just this tiny step involved a huge expansion of what mathematics has to say about the world, its connection with the world. That this is what it gives suddenly makes mathematics philosophically important. Why, to be a philosopher is the implication, you have to know math. This is that key, the transformative moment happening just innocently in this discussion of Dante. So Mark's contribution to understanding the mystery of the Galilean moment is that he shows us just how this small step made possible by Galileo's training in the humanities was at once innocuous and momentous. It helps us understand the origins of what Mark calls Galileo's early mathematical philosophy and how this philosophy was grounded in the humanities. But let me talk about yet another way in which the humanities contributed to the formation of the Galilean moment, concerning Galileo's training specifically as a musician and his abilities specifically as an experimenter. Peter Pessek's important new book, Music and the Making of Modern Science, devotes only a few pages to Galileo, and those pages concern, oddly enough, the heliocentric theory in chapter 3 of Peter's book, mainly because Peter was relying only on Galileo's own explicit statements about music, and Galileo's own explicit statements pertain basically to how he used the new science to think about music, rather than how the music helped formulate might have influenced the development of the new science. The Galilean scholar Stillman Drake makes much of what he sees as the strong influence of Dad, Galileo's father, on Galileo, but much of this is only persuasive speculation rather than documentation. But I want to point out how Galileo's musical training seems to have influenced not only his conception of the relation of mathematics to the world, but also his experimental abilities. Now, the most obvious connection can be found in the inclined plane experiment described in the two new sciences. This is what science teachers often call the alpha or primal experiment. It's frequently the first demonstration experiment that students actually do in introductory physics classes. And in many respects, it was the first modern scientific experiment in which an inquirer, Galileo, systematically planned, staged, and observed a series of actions in order to discover a mathematical law. What happens, Galileo asked himself, when an object is released to fall freely? You drop a piece of chalk. Does it pick up speed in a smooth fashion? Does it jump to a natural uniform speed? Does it collect speed, make some transition to a uniform speed? But how do you find out about this? If you drop something like a piece of chalk or a coin, it just falls too quickly to keep track of. How to arrange things so you can get the answer with more precision? Now, Aristotle had been interested in this question, of course, had examined bodies in motion in detail. Motion is the key to nature for Aristotle, and evidently noting the way that objects, if you drop an object, you can't keep track with your naked eye. So how do you slow it down so that you can figure out what's happening? Well, of course, the obvious way is just let it fall in water and see what happens when it falls in water. So Aristotle evidently experimented in this way and concluded correctly and plausibly that the speed of a body is uniform, it's proportional to its weight, and it would be infinite in the absence of resisting medium. But perfectly logical conclusion based on the way he was setting up the experiment. But Galileo became convinced that studying the motion of bodies and liquids obscured rather than clarified the issue. He sought to dilute, as it were, the influence of gravity by rolling balls down inclined planes and seeing how their rate changed as the incline steepened. This, he hoped, would lead him to solve the case for freely falling bodies. I mean, if I had a PowerPoint, I'd show you take a ball rolling down a plane like this, then like this, then like this, and if you can measure the speeds, you can eventually deduce how the object will fall if you just let it fall freely. Okay. Galileo's notebooks and correspondence show that by 1604, he had discovered the law of acceleration he was looking for, thanks to his experimentation on inclined planes, namely the distance traversed by an object, regardless of the angle of the incline, depends on the square of the time it's accelerated. This, of course, is now known as Galileo's law, and dressed up in the form of an equation, d equals 1/2 at squared, but of course it wasn't written in this equation at the time, but rather as a proportion. A lot of this early work was. I mean, Newton didn't write F equals ma. That was only, F equals ma was written first by Euler 100 years later. Newton put it in the form of a proportion. Equations were what we now teach as equations were written quite differently then. So what's remarkable about this is that Galileo was the first to realize that time was the important variable to watch. Now, that experiment and its use of time as a variable created problems for certain historians of science who just could not believe that Galileo could keep sufficiently precise track of the short time intervals involved with the instruments at his disposal. The chief device at his disposal was a water timer. For measuring short times, he used a water timer in which you took an amount of liquid in a container, and at the beginning of the interval, you removed your finger, water would fall out, then at the end, you'd stick your finger back, and then you'd measure the amount of water, and then you'd be able to deduce the time interval from that. That was the clock available, the timing device available to Galileo at the time. Such timers were notoriously difficult to use accurately over short time intervals. As a result, many science historians not only disbelieved, but even ridiculed Galileo's claim to have used a water timer to measure what he calls the 10th part of a pulse beat, or approximately a tenth of a second, 0.1 seconds. Could he do that using a water timer? The most outspoken critic was Alexander Koyré, a Galileo specialist. In 1953, Koyré wrote of the amazing and pitiful poverty of the experimental means at Galileo's disposal, and he derided the inclined plane experiment. And let me quote Koyré. "A bronze ball rolling down a smoothed and polished wooden groove, a vessel of water with a small hole through which it runs out and which one collects in a small glass in order to weigh it afterwards and thus measure the times of descent. What an accumulation of sources of error and inexactitude. It is obvious that the Galilean experiments are completely worthless. The very perfection of their results is a rigorous proof of their incorrection." Well, enter Thomas Settle, a struggling graduate student in the history of science at Cornell. Settle decided to reconstruct the experiment using equipment and procedures that were available to Galileo. With some wooden blocks, a flower pot, a small glass pipe, water, some balls, and a lot of practice and graduate student bravado, Settle managed to get excellent data and concluded that the experiment was feasible. If I had the PowerPoint, I'd show sort of a setup of Settle's experiment, which was published in Science magazine in 1961. So he managed to do it. This grad student managed to do it, but it required a lot of training. I mean, that's the part of what being an experimenter is. A lot of modern-day experimenters with their very precise equipment look back on early historical experiments and say, "Oh, they couldn't have done that at the precision of the time." Well, part of the skill of being an experimenter is you get more out of the equipment than seems possible. And Settle managed to do that as a grad student. Still, even after Settle, many science historians remained unconvinced. While they accepted that Galileo might have used such equipment to demonstrate the law, they doubted that he would have used it to establish the law in the first place. They assumed that Galileo had first discovered the mathematical law by some form of abstract reasoning, then built the device he described to demonstrate it. This is kind of a theory-dominated version of science. So he discovered, this has to be true, then you build this as a demonstration. Remember, what we know of it is through this account in the two new sciences. So the reason for skepticism, again, was uncertainty introduced by the water timers. In the 1970s, Stillman Drake challenged this assumption as well. By carefully studying a page of Galileo's notebooks, Drake concluded that Galileo actually had arrived at the law using the inclined plane method, but by marking out the time in a way that took advantage of his musical training. A competent lute player, Galileo could keep a beat precisely. A good musician can easily tap out a rhythm more accurately than any existing water timer could measure. Drake determined that Galileo had set frets into the track of the inclined plane, movable gut strings of the kind used on early string instruments. When a ball was rolled down the track and passed over a fret, you could hear a slight clicking noise. And Galileo, in Drake's speculative but very plausible reconstruction, then adjusted the frets so that a ball released at the top struck the frets in a regular tempo, which for the typical song of the day was just over half a second per beat. Once Galileo had marked out fairly exact time intervals, thanks to his musical ear, all he would have to do would be to measure the distances between the frets. These grew steadily longer as the ball picked up speed, illustrating the 1-3-5 progression and allowing him to compose the more elaborate experiment described in Two New Sciences and reconstructed by Galileo. So Galileo's musical training, in short, made him a more skilled and more ingenious experimenter than science historians had given him credit for. Now, many of you from Stony Brook may remember Clifford Schwartz, right? Some of you remember Cliff Schwartz, right? Who, a founding member of Stony Brook's physics department, and for nearly 30 years, editor of the physics teacher. Cliff had uncanny ways of drawing out the abilities of his students so they could do seemingly impossible things. And he also liked to challenge them with various experiments of his own design and some historical experiments. And he particularly liked the inclined plane experiment and would begin by canvassing the class for musicians, and there were usually a few, and then he would prefer drummers, and he would then set up the experiment in the way Drake described, using the beat set up by the musician to establish the regularity of the rhythm as the rolling balls passed the frets. In this way, tapping the musical abilities of his fledgling experimenters, it was always possible to derive Galileo's law from the data. So experimental skill, what the Germans call Fingerspitzengefühl, is difficult to pin down and to talk about, but I think Drake's highly plausible recreation of Galileo's procedures in setting up the inclined plane experiment shows yet another way in which Galileo's training in the humanities fostered a scientific practice in a way that brought a seemingly impossible conclusion within his grasp. So humanities training made him not just a better theorist, but also a better experimenter. Now, at the beginning, I mentioned that the humanities were connected with the Galilean moment in two ways. One was that his training in the humanities was key to the work that led to it. Another, though, is the challenge that the Galilean moment then began to pose for the humanities. And this is a much longer issue that I'll just mention a little bit here. But let me frame this challenge by recalling Galileo's famous image that Mark talked about of a book of nature written in mathematical characters. The idea of a book of nature did not begin with Galileo. As Peter Harrison points out in his book, The Bible, Protestantism, and the Rise of Natural Science, liking the study of nature to reading a book was a Christian tradition that at the time of Galileo's time was already hundreds of years old. The novelty that he brought to the image was that the text was now written in mathematical figures. So Galileo, in fact, Harrison's book is wonderful because it shows how the Bible was viewed as integral to reading the book and determining the meaning of nature. Galileo chose his image wisely. Its roots were deep in Western metaphysics and theology. First, it used the traditional idea that God revealed his power, glory, and truth in the world. Second, it relied on the equally traditional notion that the Bible cannot go against clear demonstrations of logic or the senses. And finally, it appealed to the time-honored metaphor of nature as a book. Galileo was on solid theological ground. But Galileo, perhaps without being fully aware of it, had stood the old image on its head. The image of the book of nature now implied something almost opposite of what it had before, namely that the signs of nature had their own self-contained meaning. That is, to understand nature, one did not need to rely on the Bible as an allegorical tool, as the earlier image had implied. Studying nature was now an independent activity best carried out by a separate professional class of scholars. If anything, the book of nature now became the primary text, the blueprint written in technical language, and the scripture, the user's manual, written in popular language. So when Galileo proposed the image, all that he said was, hey, there are two books out here, they can't conflict one another because they have the same author, so he's putting them on parallel to one another. But the implications of his discovery is that the book of nature written in mathematical figures was now the primary text, really, and the user's manual had to dominate the user's manual rather than vice versa. Or rather than a strict parallel. So it had that little implication that Galileo maybe was aware of, but didn't make explicit. So Galileo could then use the image to defend not only himself, but all scientists, suggesting that he was defending a whole professional class of scientists, saying that they were as authoritative as the clergy. The Book of Nature and those natural philosophers who interpreted it, writes Harrison, assumed part of the role previously played by the sacraments and the ordained priesthood. So clever wielding of this old image. But Galileo's powerful image, which lies at the core of the Galilean moment, now haunts us today. You can't just take it out and put it into our context and read it the same way. One reason is that it implies the existence of an ultimate coherent truth, a complete text or final theory. While many scientists may believe this, it's ultimately only a belief. Isn't it far likelier that we will endlessly find more in nature than our concepts and technology continue to evolve? That this book will, as we read it, will continue to change the way that it's written. Furthermore, the image suggests that the text of the Book of Nature was the conscious, explicit product that it had a divine origin. The idea that the world was the oeuvre of a superhuman author was the precursor to the idea that it was the engineering project of an intelligent designer. Mark referred to Aggiunti's letter, which is really interesting, to Galileo about reading geometry and then having to give up Aristotle. But we'll generalize that. The implication is that after science, what's left for philosophy? That's the ultimate question. That's the ultimate challenge. I see an echo of this on page 1 of Hawking's with Mlodino's book, best-selling book, The Grand Design, where he says philosophy is dead. All the interesting questions about how the world works are addressed by science. So philosophy is dead. Science becomes the torch of knowledge. Is the torch of knowledge, as Hawking says. So but finally, the self-contained meaning of this text is a strange one in that it's devoid of human designs, desires, and purposes. What's the connection between it and the world we live in, what the philosophers call the lived world, one that's so full of human designs, desires, and purposes? This is the challenge that the Galilean moment posed and continues to pose to the humanities. This Galilean text, the world it describes, and the world is more fully fleshed out by Newton. It describes a world in which the only things that inhabit this world are masses. The only thing they do is move, and they move under the influence of forces. So in order to calculate anything, you just establish their position and momentum, and then you have a grand calculation machine to figure out what happened before and what comes after. So this world describes a world that's not our own and not one we could live in. And yet, of course, it has lots of implications for understanding our own world. It's an abstract world that appears by changing what we look at and how we look at it. It's a fishbowl-like world, seen from the outside, closed off from our own, but whose events disclose to us much about our world. But what exactly is the relation between that fishbowl world and our own? The great temptation, as the philosopher Edmund Husserl observed in his book, The Crisis of European Sciences, is that this world easily seduces us into thinking that it is the real world. And Husserl uses Galileo as the figure for the constructor of this world. We begin to neglect questions and issues that should orient us in the lived world. It has a heavy cost, Husserl says. We expect that these questions and issues are going to be resolved in the abstract Galilean world, and that the Galilean world doesn't have answers to all these questions and winds up letting us down. And this leads, Husserl says, to increased skepticism, irrationalism, and mysticism with respect to science, which in his day was manifested most dangerously in the form of Nazism, and by our own and other forms of skepticism and irrationalism. So to head this off again, Husserl says, we have to describe how these two worlds are related, how the Galilean world of mathematical figures is related to our own, what's lost, what's gained in the transition between these two worlds. The humanities are still struggling with this, I think, and this is my conclusion. So, and this is the most important legacy of the Galilean world left for our own. So the Galilean moment, then, to conclude, not only sprang from the humanities, but it also bequeathed to the humanities a challenge, which is how to describe the world how the world that it describes is related to our own, and the humanities will have to significantly reappraise its nature and goals in order to cope with this challenge. Thank you.